Hey guys, welcome to Unit 6. Today we're going to start with the first lesson of the unit. It is continuity at a point. Our objective today is explaining the continuity, discontinuity of a function at a particular point by using the definition of continuity. I want you to pause the video and try the warm-up. So the graph is given to us and we have to find these answers to the questions that are given to us. So part A, it says limit as x approaches 2 f of x. So as x is approaching 2, from the left it is approaching 6, right? It is 6, yep, it is 6. And from the right, if I was to trace it, as x is approaching 2, y is approaching 4. So this would be the left is not equal to the right, so this is does not exist, right? B, f of 2. F of 2 would be this point because it's a filled circle, so this is 6. And C is limit as x approaches, I'm just going to erase that. Limit as x approaches 5 from the left. If I do it from the left, it's approaching, what value is that? 7? Yes, it is 7. And from the right, it is approaching the same number, so this would be 7. And f of 5, there's a hole and a filled circle, so that is 7, right? That was our last unit, limits. So now what are we doing today? Is f of x continuous at x equals 2, y or y not? So there are some parts to it. So at x equals 2, what is happening? If I was to sketch this, I'm going to take a highlighter. If I was to sketch this, do I have to pick my pencil? I had to pick my pencil and then I continue with sketching my graph. So it is not continuous. So we'll write no. Because if we check based on our limits, right, the limit set did not exist, so limit as x approaches 2 from the left is not same as limit as x approaches 2 from the right. That's the mathematical definition of it, and it's not equal to f of 2. If they all were equal, then you know it is continuous. So the next one, is f of x continuous at x equals 5? So let's check. It is, right? We just did that when we found the limit at as x approaches 5. It is the same. These are the same numbers. So yes, because limit as x approaches 5 from the left is equal to limit as x approaches 5 from the right, and it is same thing as f of 5. So that's the definition of continuity. So continuity of a function at a point. Most of the applications of calculus require the functions to be continuous. A function is continuous if you can draw it in one motion without picking up your pencil. So these are a few examples given to us. Okay, definition of continuity at a point. So let's write that down. A function is continuous at a point x equals c if the following is true. It is limit, very similar to what we wrote, c approaches c from the left of f of x is same as f of c is same as limit as x approaches c from the right of f of x. Basically, if I was to translate in simple English, is if the left limit is equal to the value of the function is equal to the right limit. If it is true, then it is continuous. That's what you need to remember, right? In other words, a function is continuous at a point if and only if, I'm just going to change color, if the function value and the limit value are the same at that point. Okay, so now there are 4 types of discontinuities which you must know, and we'll also learn how to eliminate some of them. So the first one is a removable or point discontinuity occurs when a function has a hole. The limit exists but does not equal to the value of the function. So example 1 is given to us, and it's saying where is f of x discontinuous. Anytime we think about discontinuity, we think about holes or vertical asymptotes, right? So we take a denominator, set it equal to 0, and this would be x equals -4. So now how can we tell the difference between a hole and a vertical asymptote? So let me tell you. If I was to take my denominator, my whole function, and I factor it out, and my denominator cancels, right? Then there's a hole. If it does not cancel, then there is a vertical asymptote. So let's write that down. Can cancel denominator. And I'll do an example which will make more sense. And vertical asymptote is cannot get rid of the denominator. So I'm going to go back to this question. Here we said it's discontinuous, or we're thinking there could be an asymptote at x equals -4. But now we're going to decide whether it's going to be an asymptote or a hole. We know it's undefined. There is something wrong at x equals 4, but what is it? How do we find that? So what you do is you factor the numerator and the denominator. So the numerator can be factored to x plus 7 and x plus 4, and my denominator is just x plus 4. Now what happens? The x plus 4's cancel out. So I was able to get rid, right, of the x plus 4, my denominator. I canceled the denominator. That's what I meant by canceling the denominator. This means there's a hole at x equals -4. So what I did was actually I removed my discontinuity, right? It got cancelled, and that's why there's a hole at x equals -4. I want to do actually another example, and that is x minus 3 over x squared minus 9. So the first thing you're going to do is factor it. You can't say it has a vertical asymptote at x minus 3 and plus 3 till you simplify it completely, okay? So I'm going to simplify it. It'll be x minus 3, x plus 3, right? That's dots. Now what happens is your x minus 3's cancel out. So what does this mean? That at x equals, so there's a hole at x equals 3, and this is what? A vertical asymptote at x equals -3. Why is it a vertical asymptote? Because I was not able to get rid of that denominator, but x minus 3, I was able to cancel it out, so there is a hole. Okay, so that is why it's called the removable discontinuity, as the name suggests, because we're able to remove it. We can remove the discontinuity by extending. Let's write that down. I would say extending or redefining the whole function. Extending, or I can also say redefining the function in order to fill the hole. And how do we do that? So you write it as a piecewise function. I'm going to rewrite it. You write the first function as it is, x squared plus 11x plus 28 over x plus 4, and x is not equal to -4. And now after you removed the discontinuity, we got this, right? What did we get? What are we left with? Just x plus 7 over, no, it's not over, it's just x plus 7, and here x is equal to -4, right? So this is how we write the function or remove the discontinuity. I just want to put this in asterisks here. We need a value that closes the hole. So this was the value. Need a value that closes the hole. Okay. The second kind is a jump discontinuity. is typically caused by a piecewise function whose pieces don't meet. The limit does not exist because the left hand limit does not equal the right hand limits, which we can see here in the picture, right? There's a jump and the left limit is not equal to the right limit, so that's what a jump discontinuity is. So now, how do we make this continuity into a continuous function? Let's try example 2. Find the real number c that makes each of the following functions continuous everywhere. So how do you do this? You take your functions, the two functions, and set them equal to each other, right? Because we're trying to eliminate that gap in between them. And now substitute x with this value, the common value. So this would be 3 minus 2 equals 3 square, and that will help you find c. This would be what? 1 equals 9 plus c. C is equal to negative 8. So that's your real number c. Similarly, we're going to try b. You can pause the video and try that on your own. And what we're going to do is substitute. First set them equal to each other, and then substitute negative 1 for x equals c times negative 1 square plus 1. I get what? 3 on the right side. Negative 1 square is 1. 4 minus 1 is 3 equals c plus 1. C is equal to 2. So that's how you do this. Okay. The third kind is an infinite discontinuity. An infinite discontinuity occurs when there is a vertical asymptote, right? The limit does not exist because it is either positive or negative infinity. So here I'm gonna just try do the first one, and then I want you to pause the video and you try the others. Okay, so the first one is what? A function's given to you, and whenever we talk about vertical asymptotes, what do? We just take a denominator and set it equal to 0, right? So we have a vertical, we can't cancel anything, so there is a vertical asymptote at x equals 3. For the next one, pause the video and see if your answer matches mine. Before I even find my vertical asymptote, let's see if I can simplify it further, which I can. The numerator becomes x plus 5 and x minus 5. That's difference of 2 squares over x minus 5. What happens to your x minus 5? They cancel out, and what are you left with? Just x plus 5, right? So there is no vertical asymptote, but there is what? A hole, because you just removed that discontinuity. Hole at x equals 5, right? The next one, again, try that on your own. I can factor the denominator. I'm just going to zoom in. X minus 4 and x plus 2, right? So I'm just going to rewrite this. What happens to x plus 2's? I'm just going to rewrite it. X plus 2 over x minus 4 and x plus 2. So these cancel out. So since they're canceling, it means there is what? A hole or removable discontinuity at x equals 2, negative 2, not 2, negative 2. And there's a vertical asymptote at x equals 4. So there's two things, okay? So let's try the last page, or the last type of discontinuity. And blank discontinuity, it is the oscillating, oscillating. Discontinuity occurs when the function oscillates and has no limit as x approaches 0. The limit exists but does not equal to the value of the function. So here's an example. The graph of f of x equals sine 1 of x has a oscillating discontinuity because it's going to keep going up and down and switch between those two numbers. Okay, so these were the 4 kinds of discontinuities, and we also learned how to remove those, especially the removable one by canceling it, and the jump discontinuity by setting it equal to each other. So finish the remaining problem set. Good luck.